Start, sir.
Yeah. Yeah. Hello, students. Good evening, and welcome you to this live session on Urban Transportation Systems Planning course. This is the second live session, so I'm happy to welcome you for this live session. And so far, whatever lectures you have attended, if you have any specific doubt, anything you want me to explain, or any other thing you would like to ask me, you feel free to ask. Uh, there were some questions which were posted in the forum, discussion forum. They were related to the numerical problems which were discussed, how to go stepwise. So we tried to explain you. Uh, Other than that, if there are any question, please start posting your question, and I can start discussion based on one question that which was given here. I can see that red bus, blue bus paradox. And the students say that finally there are totally three alternatives and all are having equal utility value. So the model is telling that the probability of choosing each alternative is same, 0.33. In this way, how can we say that the model is unreasonable? And this is quite an interesting question. Uh, you see that whenever we are considering different alternatives, uh, then any improvement in one of the alternatives will have impact on the distribution, right? The way the probabilities of choosing different modes were there are there, those are going to change. But suppose, keeping aside that red bus, blue bus paradox, that again I can always discuss, there is no issue. But I am saying that even alternatives, somebody is going by car and somebody is going by taxi and then maybe uh, train and bus. Now you can clearly see that train and bus are very similar kind of modes. So what happens if there is a change in the bus fare, and if the train is also as available as another alternative, logically you expect people then to shift from more people to shift from bus to train, right? Or if it is other way, maybe train to bus, because they are very similar public transport. Now, obviously, because of the change in the transport cost, maybe travel time and other thing, some people may also shift to other modes. People may, some few may start going by taxi, uh, but majority you expect them to use the other alternative public transport. But because of this IIA property, what is really happening in IIA property? The ratio of probability of choosing two modes, as you say, probability of choosing A divided by probability of choosing B, that is only a function of the utility of A and B. So anything happens with any other alternative C or D, this ratio will remain unaltered. So always, whenever, suppose in the previous example, I say that bus fare is increased. So obviously bus is now less attractive. So people will shift from bus. But then in order to keep, because of this IIA property, the way they will shift will be controlled by that ratio. So you may find that maybe relatively less people are going to train, and maybe more are shifting to bus, shifting to car or taxi, because of this IIA property, because the ratio is constant. So any increase or decrease, it will increase. Suppose all other modes will increase, but increase in that ratio, right? Keeping this ratio unaltered. So if it is, say, probability of using car by probability of using taxi, if it is that is say 1.5, so that ratio will always remain same. So if people are shifting to this from any other third alternative, which is not this within these two alternatives, then they will be distributed in a manner so that the ratio remains constant. Now that sometimes is not logical, as I said this example, that if train and bus are there, there is no reason that why somebody who is traveling by bus will now jump to car, and majority of them will jump to car. That will not happen. They may go to the the very close alternative, that is train. So the blue bus, red bus is also an example of that kind, where everything is same. Maybe you are taking them as two alternatives, but suppose some people are going by bus today, and if another company, everything is same, and only the instead of painted as red, if it becomes blue, that doesn't mean that is a completely new. So what do you expect? Probably logically, that people who are using bus, they will only get distributed. Some will take, if they are equal in every sense, then maybe 50% of those bus users will now use blue bus, and other 50% will use, uh, um, the red one. So the total bus users may not get changed in that manner, but they will get distributed to all these red and blue buses. That's what is logical. But because of this IIA property, uh, the they will be taken like this, equal, and then all three were given 0.33 probability. So 33%, 33%, and 33% in all the three modes. So as if that you start a new bus, a lot of people leave from car and then come to bus. So that way we say that it's not very, very logical. And the IIA property is actually, why it is happening because of the IIA property. Now, if you remember, towards the end of that mode choice model, we discussed about nested logic. So what is really the nested logic? Nested logic, we tried to put together similar mode in one group. So depending on, of course, how you calibrate the model and parameter estimation, whether a nested logic is acceptable, that's a different thing. You have to estimate, you have to get convinced that the nested logic structure is proper. But the nested logic, the idea is that if I have got a lot of alternative private modes in one hand, and another hand lot of common carrier public transport mode. So anything happens with the common carrier modes, one mode the cost goes up, goes down, whatever it is, things are more likely to change within those category of modes, which are very similar, rather than happening with the other altogether other branch, which is entirely a different kind of mode, right? So that was the idea for the nested logic, and that's why the nested logic is preferred. It can partially overcome this IIA property, right? So IIA property, that's what we partially eliminate. And then when you go to more advanced kind of model, mixed logic model or random parameter logic model, that further relax the IIA property. So that was the reason. So these are all different modeling techniques and which are used effectively. Not that always, multinomial logic model is bad. Not at all. You can use MNL model for so many works. And if the nested this kind of AI property is not affecting your result, whatever you want to do, then it is okay. Now, if it is affecting and you think that a nested logic is okay for you, go for a nested logic model. If you, for other reason, other constraints, so it's like different modeling approaches are there, and every modeling approach has its own application. So you have to see that what you do. Even generally, the all modeling approaches, not only for these behavioral models, we say also there are so many types. So the later on you will learn some other advanced modeling technique. Of course, only introduction. Uh, you will see that uh, we discussed so far whatever lectures you have attended, we discussed so far this kind of behavioral model, which is multinomial logic or logic model. But then these are all basically trip-based model, right? So the four-stage planning process altogether: trip generation, trip distribution, mode choice, traffic assignment. These are all trip-based model. That means if A to B, B to C, C to D, and then D to C, C to B, and B to A, all are happening. We are all considering them as separate trip. And then taking them as separate trip, we are doing the mode choice, we are doing the route choice and everything. But this is again sometimes maybe absolutely fine, but sometimes there are interdependency, or the trips are interlinked, so they're not truly independent and separate identity. So if you are, but then that problem may not come in all contexts. Say for example, if you are going to office and coming back, perfect. Even a trip-based model is perfectly all right, right? But if you consider the person is making multiple trips, I'm going to the office, and then from office I'm going to the bank, and then or going for a lunch to some restaurant, coming back, and then evening I'm going for some shopping, or on the way back I'm doing shopping. Multiple, activities I am trying to manage. In fact, we do so, right? So then the further advancement to trip-based model is the trip chaining. Further advancement is the activity-based model, and the future of transport modeling, demand modeling is actually the activity-based model. But does it mean that every case we will go only for activity-based model? We will not go for trip-based model? The answer is no, because it will primarily get governed by the fact that what you want to get from the model. You are developing a model with something in mind, something you want to achieve. So what you want to achieve, what you expect to get from the model. Now, if I get my answer with a simple model, why I should go for more complicated thing, right? So if you have a simple fever, if paracetamol is fine, you just simply take crocin or calpol and you are all right. So that is fine. So you don't need that every time you get a fever, you immediately don't go for an antibiotic, right? But if it is required, if it is that kind of fever, which is, paracetamol is unable to, resolve or sort out the problem, then only you go for further. So it all depends. There are different modeling techniques, and here also, everywhere the alternatives are taught, alternatives are available, because they have their own application to it. In structure, when you learn, you also learn the concrete structure, you also learn steel structure. Does it mean that always we go for concrete structure or always we go for steel structure? No. Again, depending on the context, right? That under some situation you may prefer a concrete structure, and some other situation you may come out with a steel structure. You may say that no, I should go with a steel structure. The same way, somewhere you will use MNL model, somewhere you will use nested logic model, somewhere you will use even more complex test model, maybe uh, other behavioral model, for example, mixed logic or random parameter logic model. Somewhere you will altogether not go for a trip-based model, but you have to go for an activity-based model, because simply the kind of questions you are expecting to get answer from your model, maybe a trip-based model cannot give you that answer. So then that's where is the real necessity, where you will go probably to for activity-based. So that's what it should be. Every alternative method. You have studied trip distribution. The growth factor methods have its own, all this method has its own limitation, but it has its own application as well, right? So not that always you will go for a gravity model or a spatial interaction, whatever is considered, you will go. Simply suppose city network, nothing significant has happened, and you are considering in a city-wide context. 2 years back, you developed something and that model is there. You simply want to update that model, and you know nothing big really has happened in terms of development of transportation network or the transport system characteristics within these 2 years. So then it's a smart approach is just go for a simpler growth factor based model and update your methods. But same thing in another context, if within this 2 year, the metro has started its operation and quite a few routes are now being served by metro. And if you want to update, probably it's not good for you to go for or the BRTS is operational, bus rapid transit system is operational, then it cannot be good for you to go for this kind of simple technique. Probably it will be good for you to recalibrate or at least take some smaller uh, zones with respect to your specific project location, and some kind of additional effort may be worth. So everywhere it is. So all or nothing assignment is also could be applied somewhere. I mean, if it is not really a congested network, and for some kind of preliminary planning or so, you are trying to find out where and which one, which are the roads you need to improve or so. Very, very preliminary kind of thing. And you don't expect a congested network. So you can as well go for it. Maybe some approximation will be there, but then that result is fine for you. You still get your answer. But if it is a congested network, urban network, like whatever is existing in Mumbai or Kolkata or in other metro cities, and if you are doing your assignment using all of nothing, you will be wrong. You cannot apply. So the applicability will teach you different approaches about different courses, being it in transport context, being it in modeling context, being it in techniques for assignment, any kind of thing, any context, beyond even transportation engineering, structural engineering context. Uh, Foundation also, there are many types of foundation which we teach you. But you have to select for a given context whatever is my problem, whatever I am looking for, what I expect to get, and the kind of overall context, what is the best approach? And we don't, please don't try to complicate things unnecessarily. That's not necessary. You know, don't try to complicate things unless uh, complications bring some additional things. Maybe your other methods or other techniques will not be able to answer to the questions you are looking for. In that case, you apply more advanced thing. So please post your questions. If there are additional questions, I will be happy to discuss. Of course, during the regular forum also we are interacting, so you may not have really too many questions to ask, but you are welcome to ask something related to what we have taught or anything related to the course. Even if I have not taught it directly, but you want to discuss something related to transport or transport related issues and problems, and you want to know something, please feel free to. So there is no other question for the moment. Okay. From the discussion forum again, can you please explain in detail the giving example of link cost function with flow and capacity? Now, what really happens? Okay, this is also another interesting thing, that any facility, any physical facility will have a capacity. Whether you talk about a building or a godown or a road, right? Any physical facility will have a capacity. It cannot take more than that. So, as long as you load that uh, at a lower end as compared to the capacity, things will be all right. Right? You have a uh, 2-bedroom flat, 2 BR flat, 2 or 3 people are staying. That could be perfectly all right. You will feel very comfortable, probably, right? But if I load that with 10 people, then it's a problem, right? 10 people will be too much for that kind of flat, probably. Similar kind of thing when you have a say uh, 4-lane divided road, maybe each side you have 2 lanes available, right? So 2 lanes means, of course, the capacity will depend on what is the environment, roadway traffic and control condition will govern that, what will be the real service volume it can offer. But if I take even nearly idealized condition, and for simplicity, if I take that, okay, somewhere around 2000 PCU per hour per lane is the capacity. A bit on the higher side, urban roads you never get that. Maybe you will get somewhere around 1600, 1800 or something like that. But just for, okay, even if you take 1600, that means 3200 PCU per hour per direction. Now, if I load it, if my present demand is 500, what will happen? Vehicle will enjoy very high freedom of movement. So they will not feel the facility is congested, and freedom of movement means they will get enough opportunity if somebody wants to drive little faster without, of course, violating the speed limit and other thing. He or she can do that. If you want to overtake, you probably get an opportunity to overtake, and you don't feel so much stressed while driving because it's not so congested. But as I keep loading more and more vehicle on the same road, so then my volume to capacity ratio, as it increases, volume to capacity ratio increases means the volume is gradually increasing and approaching towards capacity. So when the volume to capacity ratio is very high, this thing, you started maybe in the early morning looking at the road when the traffic volume is very low, every vehicle is traveling very fast. So probably from one point to another point, you can reach in half an hour. But then as the traffic volume increases, your freedom of movement is less. So your travel speed also has to come down because the density is becoming more and you find more vehicles around you. So you cannot travel fast, right? Overall stream speed will come down. And that 30 minutes in a moderate way may take 40, 50 minutes. And even in when the whole thing is loaded almost near capacity, it is working, then you may even take 1 hour or maybe more than that to travel the same distance. That means the travel time is a function of what is your capacity, what is your demand, and also the effect of loading on a road, right? On a given facility, how the speed will reduce because of loading will also depend on the other roadway traffic and control conditions. Because the road is passing through an area, urban area, where both sides there are, a lot of pedestrians and window shoppings are happening, and some pedestrians are crossing the road, and then maybe some vehicles are also parked by the side of the road. Vis-a-vis another stretch where such kind of interference is not there, or there but at a much lower level. That will also influence, right? So for a given road, more the loading, higher will be the travel time. But on different roads, depending on the roadway traffic and control condition, the effect of impact on increase in the traffic load on the travel time may be also different, right? But let's take a given road. So a given road, the roadway traffic and control condition is same. Now, as I keep on increasing the traffic volume or traffic load, then my freedom of movement will be low, and I will have higher time, higher travel. So this is generally non-linear. Non-linear means what I say increase in the volume will reduce the travel time. I will reduce the speed and increase the travel time. So every unit increase in the volume will have some impact on the travel time. But just imagine when the volume capacity ratio is say maybe 0.1. Now 0.1 to 0.2 in that range, every unit increase may not really have that much impact on the, still probably the freedom of movement will be quite high. But if you consider a mid-range, when the volume capacity is around 0.5, maybe 0.5 to 0.6, that in that range, per unit increment in the flow, the reduction in speed will be higher than what was in the range of 0.1 to 0.2. Now, if you are going near capacity, that means somewhere around maybe 0.8, 0.9, that time, even the same unit increment will give you much higher reduction in the speed or much higher increase in the travel. So the effect of same increment in travel volume on the reduction of speed is different when the volume capacity ratio is 0.1, 0.5 and 0.9. It will be higher, more reduction in speed, more increase in the travel time as the volume to capacity ratio is higher. So the relationship is not linear, rather it is non. So if you look at the BPR function, this speed equal to free flow speed into 1 minus A into V by C to the power B, that kind of relation. Now B is taken 4.4 and it is some constant value, although they will generally depend on the prevailing roadway traffic and control condition. You take different roads, your A and B value will be calibrated value will be different. But this kind of thing, that means it is saying that to the power 4, That means as the volume to capacity ratio is increasing, your same kind of equation, if I take speed at a given volume V, then it will be free flow speed within bracket 1 minus A into V by C to the power P. Travel time also you can consider the free flow travel time into, then in that case 1 plus, because travel time will increase. We can approximate it like this, right? So the increase or decrease will happen, whatever you say, if you are taking the speed or if you are taking the time. Link cost function is normally the time we are taking. So the time will become higher as the volume to capacity ratio increases. But as I say, for every unit increase in volume or volume to capacity ratio, whatever way you want to express, you will find the reduction is not going to be same, because if I see to the power 4, 3, okay, PPR assumes 4, maybe some other calculation will give you some other value, right? So it is a nonlinear function, and it is always like. And this, because of this nonlinearity and because different links might be operating at different conditions, right? So that's why the user equilibrium and system equilibrium flows are going to be different. For example, that uh, you have a road where the travel time is less, still maybe as compared to the travel time on another long distance route. So the, as per user optimal equilibrium, still people would, even though it is congested, still people would prefer to take that shorter path because the time is still less, even though it is congested. But imagine that whatever will be the benefit, reduction in time, reduction in journey time or increase in speed because of some unloading on that congested lane, because congested lane is operating near volume to capacity ratio, say 0.9 or 0.1, almost 0.9 or 1, almost like demand equal to capacity. So that's where the increase or decrease will make lot of change in the overall travel time. But because of the same amount of loading in an uncongested segment of a longer route, the increase in travel time is not going to be that much, because maybe that is all operating near VYC ratio 0.1 or zero point 0.2. So there, if you add a little bit more volume, the travel time doesn't change that much. But here, taking out from a congested road which is operating at VYC 0.9 or 0.95, the relief will be substantial. So the gain and the loss is not going to be equal. And that's why probably the system equilibrium and user equilibrium will give you different solutions. But once if it is all linear, then anything you take, whatever is the gain, there also the loss will be the same. But that doesn't happen because different roads operate in different traffic state. VYC ratio is not same, right? And the overall link cost function is nonlinear. So the gain because of unloading on a congested road and the loss due to loading of that same volume on an uncongested road is not same. That makes basically the user optimal and system optimal solutions. And that is again the reason why we say that if it is uncongested network, that means all the links are basically operating like 0.1, 0.2, 0.3 in that range. No link is having a traffic load which is like 0.8 or 0.9. Okay. Uh, so in that context, we say that user and system optimal equilibrium will give you the same solution. That's what it is. So thank you so much. That way, if there is no other question on YouTube, then we may conclude the section, conclude the session. So I think thank you. Still, I give you a minute. If you have any question, please post. If not, then we would like to conclude this live session. And I would like to express my sincere thanks to you for joining this course and joining this live session. Uh, in every course, we can only teach a little bit. Only we try to give you some basic understanding, uh, basic inputs to uh, stimulate your thought process and the way you look at it. So the way you look at the urban transport system, the urban traffic system, everybody gets a problem. You ask anybody urban transportation, traffic problem, everybody can say, because everybody faces. But when you, with an understanding, you look at the traffic system and look at the urban transport system, things look very different. So only through the course we try to create an orientation in your mind so that you look with a different eye, with a different viewpoint, right? So once again, thank you so much. And since there is no other question, so I would like to conclude.